Hello learners, welcome to this course on embedded system design using PIC16F877 microcontroller. In this tutorial, I will be discussing about on how to control the position of a servo motor based upon the ADC signal. So let us start with the fundamentals of a servo motor. A servo motor can be used to rotate the shaft with great precision. So great precision in the sense we can position the servo motor exactly to a particular degrees. So I can move the servo motor to 10 degrees, 20 degrees, 30 degrees, etc. So we can position the shaft of the servo motor precisely. So depending upon the power scheme, whether AC or DC, we have a DC servo motor or AC servo motor. So here I show a typical servo motor which comes with different types of shaft. When you look at the internal architecture of the servo motor, it consists of a DC motor. So in order to reduce the speed of a DC motor, a gear system is introduced and it is connected to the shaft of the DC motor. So thereby the speed of the DC motor gets reduced and the position of the servo motor shaft is measured using a position sensor or using a potentiometer. Then this signal, the sensor output, is compared with your reference input signal and an error signal is generated. And this error signal is used to vary the electrical input to the DC motor. So thereby the shaft will go to the desired position and it will stop there. Since it is a closed loop mechanism, closed loop feedback system, precise positioning of the shaft is possible. So when you look at the wiring connection of a servo motor, it consists of three lines, orange line, red line and brown line. So a red line needs to be connected to a supply voltage, brown line needs to be connected to a ground line. And the orange line specifies a PWM line, pulse width modulated line. So the position of the servo motor shaft can be achieved by providing a PWM signal to the orange line. So PWM is nothing but pulse width modulated signal where we generate a square wave with different duty cycle. So duty cycle is nothing but for how long we have on time in a total time period. So for example, the total time period is nothing but the on time plus off time. So here if I see in the first waveform, for the 50% of the time we have on time and 50% of the time we have off time out of total time period. So thereby this signal A is termed as 50% duty cycle. In the second case, signal B, you can see for only 10% of the total time period we have on time, remaining 90% we have off time. So signal B is with 10% duty cycle. In the third case, signal C, 30% on time, 70% off time. Signal D with 70% on time and 30% off time. So by producing the PWM signal, I can vary the shaft. So we have servo motors which works with different on time of a pulse. So for example, one type of a servo motor where we have a angle variation from minus 90 degree to plus 90 degree. In order for my servo motor shaft to go to minus 90 degree, we have to produce an on time of 600 microsecond. To make the servo shaft to go to plus 90 degree, we have to produce an on time of 2400 microsecond. And the total time period, on time plus on time, off time will be equal to 20 milliseconds. So thereby, if I want to have a 45 degree movement, in that case, I need to calculate how much on time I should give so that I get 1 degree movement. So if I see the total angle variation, which is from minus 90 to plus 90, which is about 180 degrees. For 180 degree movement, my on time variation is from 2400 minus 600, which is about 1800 microsecond. So 1800 microsecond divided by 180 degrees, which gives 10 microsecond. So for each degree, I should have a on time of 10 microseconds. So in order for our shaft to go to minus 45 degrees, then I should have a variation of about 45 degrees here. From minus 90 to minus 45, we have a 45 degree variation. So we have already calculated for each degree, I need to have an on time of 10 microsecond. So 45 into 10, which gives about 450 microsecond. So this 450 microsecond is added with the initial 600 microsecond to get 1050 microsecond. So thereby the on time of a pulse for each and every position of a shaft can be calculated, and accordingly it can be programmed. So certain other servo motors, it works with a range of 1 millisecond on time to 2 millisecond on time. So 1 millisecond on time means the servo can move to 0 degrees, 2 millisecond on time the servo can move to 180 degrees. So we have to look at the data sheet of the servo motor to see which on time will produce a minus 90 degree variation and which on time will produce a plus 90 degree variation. So that we need to understand from the data sheet. So in this program, what we are going to do is we are going to position the servo motor shaft depending upon the ADC signal. So I am going to connect a potentiometer to channel 0 of PIC16F877 microcontroller. So channel 0 is at RA0 or AN0. So the potentiometer data is connected to your PIC16F877 microcontroller, which has a 10-bit ADC. Depending upon the 10-bit value, I am going to produce the on time required for a PWM signal through this RD0 line. So this RD0 line is a PWM line connected to your servo motor, and the power supply is provided to the servo motor. So for this program, I am going to use Micro C Pro for PIC as an IDE, where we will be building our embedded C program, convert this embedded C program into a hexadecimal file, and our hardware will be realized in Proteus 8 Professional, and the converted hexadecimal file from IDE will be imported onto the Proteus 8 environment. Then we try to check the logic. So first let us go and build the circuit using Proteus 8 Professional. So let me create a new project. Select a location for your project. Select a name for a project. So I have selected the location for the project, select the name for the project, press next. Select a schematic where we are going to build the circuit. So I am going to use a default schematic, press next. We are not going to create a PCB layout, so I am going to leave it as it is. No firmware is used, press next, only schematic is selected, press finish. So this is the position where we are going to build the circuit. In order to build the circuit, first thing is I need to select the components. So I go to PIC device, PIC16F877. So select the microcontroller, double click on it, it will get added to your list. Then I require a servo motor. I am going to take a PWM based servo motor, add it to the list. Similarly, you select all the components. Crystal, capacitor, switch, resistor, potentiometer, pot. I select pot HG, add it to the list. So these are some of the components which I require for building the circuit. Once we have selected all the components, press OK. So now we have selected the components, use these components to build the circuit. First let me select the microcontroller, place it onto the circuit. I am going to connect the crystal, select the crystal, I am going to rotate it, place it onto the circuit, connect the crystal one hand to pin number 13, another end connect it to pin number 14. And we need to connect the capacitors to the crystal, so thereby a stable frequency will be generated. So connect capacitors to the crystal. So a value of 33 picofarad or 22 picofarad can be used. So the other end of the capacitor, I am going to connect it to the ground. Go to terminals mode, select ground, place it onto the circuit, connect it. So I can select a value of 33 picofarad, right click on the components, choose a value. I am going to use 33 picofarad for the capacitor. So I am going to use a crystal frequency of 20 megahertz. So I select 20 megahertz crystal frequency. So up to 20 megahertz we can connect. So I am going to use 20 megahertz crystal. So this completes the oscillator part. Now let us build the reset circuit. Again go to components mode, select the switch. I am going to rotate the switch, place it onto the circuit, resistor, place it onto the circuit, connect the resistor one end to the switch, other end of the resistor I need to connect it to a supply. Go to terminals mode, select power, place it onto the circuit, connect it. Same way other end of the switch I am going to connect the ground. So connect it to the ground. And the intermediate point I am going to connect it to memory clear line, which is a reset line. Memory clear is an active low signal. So by default this pin will be at logic high. Whenever I close the switch, this pin will go to logic low, which means the reset operation will be carried out. So let me release the switch. So this completes the reset part. Now let us connect the potentiometer to channel 0 of your microcontroller. Go to components mode, select the potentiometer, place it onto the circuit. The center point I am going to connect it to RA0, AN0, channel 0 of your ADC. So one end of the potentiometer I need to connect to supply, other end I need to connect it to ground. So this completes the potentiometer part. Next thing is we need to connect the servo motor. Again go to components mode, PWM servo, place it onto the circuit. Connect the RD0 line to the PWM line. PWM line is the center line of your motor, and the top line is your power supply line. Go to terminals mode, select power, place it onto the circuit, connect it to the supply line, and the ground, place it onto the circuit, connect it to the third line. So this completes our hardware part. One more thing we have to do is we have to set the on time and off time for the servo motor. So in order to do that, select the servo motor, right click, edit properties. So here you can see from minimum angle is minus 90 degree and maximum angle is plus 90 degree. The rotation speed is about 60 rpm. And what should be the minimum control pulse and maximum control pulse? So by default it is having 1 millisecond on time for minus 90 degree, 2 millisecond on time for plus 90 degree. So I am going to change it to 0.6 microsecond, sorry, 0.6 millisecond, which is equal to 600 microsecond. Same way 2.4 millisecond, which is equal to 2400 microsecond. So my minus 90 degree will be achieved by generating an on time of 0.6 millisecond. Then plus 90 degree will be achieved by producing an on time of 2.4 millisecond, which is equal to 2400 microsecond. So let me connect an oscilloscope so that we can visualize the PWM signal. So we can go on the left side, we can pick the devices. So go to the devices, select the oscilloscope, place it onto your circuit. So in order to visualize the PWM signal, I am going to connect channel A to this RD0 line. Same way, to measure the voltage across this potentiometer, I am going to use a voltage probe. So I can go to this probe mode. In probe mode, I have voltage measurement. So take that voltage, connect it to your circuit. Okay, so I can measure the voltage across this point. So this completes the circuit part. So let us save the project. Now let us go and build the program in micro C. In micro C, first let me create a new project, a standard project. Select a location for the project. Give a name for the project. So I am going to give a name ADC underscore servo. Select the device for which the program is going to be done and the clock frequency. So clock frequency, I am going to set it as 20 megahertz. So select the location, give a name for the project, select the microcontroller IC and the device clock frequency. Press next. We don't have files right now, so press finish. So this is the location where we are going to write the program. So let me save this file with the name ADC underscore servo with an extension of .c. Press save. So let me take the program. Paste it onto this window. So let us save the program. Now let us visualize it. So here I have a main program. Since we have connected servo motor to RD0, I need to specify the port D as output pin. So in order to do that, we have a data direction register which is TRISD. So TRISD is associated with port D. So TRISD, if I put a value of 0, then the corresponding pin will be configured as output pin. If I put the value as 1, then it will be configured as input. Since we have connected a servo motor which is an output device, I specify it as 0x00, which means all the port D lines are configured as output pins. A potentiometer is connected to RA0, AM0. So that potentiometer is an input device. So I need to set it to input. So for that, I make use of this 0x01, which means 0, 0, 0, 0, 0, 0, 0, 1. So this 1 indicates the RA0, AM0 pin is configured as an input pin. So that is done by your TRISA. TRISA equal to 0x01. Then in a while loop, I am going to read the channel 0. So we get a 10-bit value as a result after the conversion process. So the 10-bit value resides in ADC underscore value. So my value will vary between 0 to 1023. So if my input voltage is 0 volt, I get a value of 0. If my input voltage is 5 volt, I get a value of 1023. Since we have a 10-bit ADC, so 2 power 10 is 1024. So my values changes from 0 to 1023. Now this 0 to 1023, I should convert it into 0 to 1800. Right? So 0 to 1800 I need to convert it. So 0 to 1023 should be mapped to 0 to 1800. Why? Because my angle of movement from minus 90 to plus 90, the on-time variation is about 1800 microseconds. So I need to map it. So in order to do that, so we take 1800 microsecond divided by 1024, which gives about to be 1.757. So I need to multiply this value. I need to multiply this value, ADC value, with 1.758 to get a value between 0 to 1800. For example, if my ADC value is 0, in that case what happens? 0 into 1.758, it will be 0. Then the 0 will be there in the map underscore ADC underscore value, and this is added with 600. So I get an on time of 600 microsecond. So if my ADC value is 1023, so 1023 in the sense, so 1023 into 1.758, which is equal to almost approximately it is equivalent to 1800 microsecond. So we get a 1800 microsecond. When I add this 1800 microsecond with 600, I get 2400 microsecond. So we can vary the on time of a servo motor from 600 microsecond to 2400 microsecond. So this on time is given to this servo underscore PWM function. So here we have the servo underscore PWM function. So where I set a on time for the prescribed time period, which is the value sent from here, and the off time for 20 milliseconds. So in order to create the microsecond order delay, we have created our own function v delay underscore us. So which is given here, v delay underscore us, which makes of a clock frequency. So we have connected a 20 megahertz clock, so which is right shifted 2 times, which means it is equivalent to 20 megahertz divided by 4, so it becomes 5 megahertz. So 5 megahertz is used to compute the on time of a pulse with microsecond order. So this function is used to create a delay of microsecond order. Then this function is used to create the on time of a pulse. So for example, here if I get 600 microsecond, then a 600 microsecond delay will be generated by this function. And during the delay, my OD will be on. Then it goes to off for 20 milliseconds. And we generate this pulse again and again for about 20 times. We generate it, which indicates that our servo motor is a slow device. It might recognize a single pulse. If I try to send multiple number of pulses, at least few times it might recognize and it can go to the desired position. So there is no harm in producing multiple number of pulses, because when it recognizes for the first time, the shaft will go to the desired position. When it recognizes for the second time, third time also, there will not be any change, because already the shaft is in the desired position. So thereby, precise positioning of the shaft can be achieved. So let us include the libraries required for executing this function. So go to micro E libraries. In system libraries, we are using a ADC function here. So I need to include the ADC library. Then I am using a floor function. So floor function is available in the math library. So in the math library, you have a floor function. So I need to include this math library. So once I have included the necessary libraries, I can build the circuit. So building, it checks for errors, and also it converts the embedded C program into a hexadecimal file. So there are no errors, so it got converted into a hexadecimal file. So now let us go to Proteus environment, import the hexadecimal file, right click on the IC, edit properties, select the program file. So go to micro C, ADC underscore servo. Processor clock frequency, we have used 20 megahertz. So select the program file, select the processor clock frequency, press OK. So now we have imported the hexadecimal file onto the microcontroller. Now let us check whether the circuit is working properly or not. Press the play button. So here you can see, right now the voltage is 2.5 volt. 2.5 volt, you can see from the voltage probe, 2.5 volt is given, 50%. So total voltage is 5 volt. So it is at the center. So 2.5 volt is being generated. And you can see the shaft is at some 3 degrees. So now if I vary the potentiometer, you can see the voltage changes here. Okay, so I am increasing right now. You can also see the shaft position of the servo motor gets changed. It is going towards plus 90 degree. As I start increasing it, you can see the shaft position is moving. When it reaches 100% voltage, then the shaft goes to plus 90 degree. You can also visualize the pulse width here. Okay, so here the pulse width you can see from the channel A. So when I start decreasing it, you can see the pulse width gets reduced. So when I start decreasing it, you can visualize this. The pulse width is reducing. The PWM signal pulse width is getting reduced. And you can also visualize the shaft position. So shaft position, when my voltage is 0 volt, it goes to almost close to minus 90 degrees. So here we are trying to generate the PWM signal based upon the potentiometer content. Okay, so you can visualize how the on time of a pulse varies and how the shaft position of the servo motor gets changed. So in this program, I have discussed about on how to control the position of a servo motor from a potentiometer content. So this potentiometer can be any sensor. So any sensor, something like a temperature sensor, pressure sensor, so which gives a corresponding voltage value with respect to the physical quantity. So those sensors can be used for controlling the position of the shaft of a servo motor. So thanks for watching. Please subscribe for more technical learning. Thank you.